SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process. Chronic consumerism is consuming the cultural heritage of Mother India at this moment at an alarming rate. Why I am saying you people should take care of it? Let us now recall what we learned in the last lecture. We basically looked at how to handle, the diffusivity, particularly for momentum and the heat transfer. So, we have derived constitutive equation for momentum transfer, right, and also the heat transfer, right. And today we will be looking at the mass transfer. If you look at mass transfer, like it is due to the molecular motions. And the very example of that, suppose some of you might be using perfume. Suppose you are having perfume, but I could smell that you are having perfume, provided I am having a good nose, or the sensor is good enough. And there will be transfer of mass, and that mass transfer takes place because of what? Because of what you call the concentration gradient. Let us consider in the similar way that we have dealt with, considering the kind of space where there is a gradient. For example, if I consider some region YD, and let us say there is some water in this, we are having porous, which is at kind of a gaseous state, that means steam, right, is saturated steam, and this is having here, and this is of course 0. At T is equal to 0, there is nothing, like kind of things, there is no water as such, but air may be there, right. You cannot avoid air as such unless you make it vacuum. And let us say in this plate, in some region here, which I will be using so that 0 water vapor will be there. How can you conduct experiment? I can have something which can absorb the water moisture, that is basically silica gel I can use, and then some kind of this thing which will keep it, and suddenly at T is equal to 0 I will start. Then what will happen? That there will be what you call this concentration gradient will be existing here between this upper plate, that is y directions here, right, and between these two plates, and there will be the mass will be transferring because the concentration gradient is there. Therefore, this concentration will be changing due to the molecular motion, and the mass flux, if you look at it is goes on changing with respect to time. It may be different profiles, right, it may be different profiles kind of things as the time increases, right. So, what will happen that if a lot of time is elapsed, then it will be attaining a steady state values, right, and the final distribution of concentration in a steady state, the profile will be looking like that. If I consider this as a x and this is your y direction, the mass flux is proportional to the concentration Ca, which is here, right, and of course this will be at a 0 concentration kind of things. So, therefore, this will be let us consider as a mole fraction, right, because number of moles per unit volumes is basically what we call the concentration. So, therefore, the mole fractions of what you call A, if I say this is space is A, is proportional to C A by Y. I can say this is D, I am using D is diffusivity, the distance, right, and that is proportional to C A divided by 0 minus Y is proportional to D C A by D Y. Right, if I put this thing as a mass flux, what I will have to do, basically I will have to say that I will multiply these things, and I can write down, let me first write down this A is equal to diffusivity dAV, minus sign will be there, and dCA by dy, right. So, I can say this is equation 1, and if I say I want to have a mass flux, what I will get? I will basically multiply it by W A here, and this side I will multiply it by W molecular weight of A, right. This is molecular so then I can write down as this is mass flux of A is equal to minus dAB MWA DC right. And now I will be more interested to express this in terms of the density, right. For that I will use an ideal gas, right. For an ideal gas, we know that Ca, right, is nothing but your Na by V is equal to Pa by Rut. Pa is the partial pressure of species A, right. And similarly, I can write down Pa is rho A RUT by molecular weight of A, right. And if you look at this, in place of Ca, I will be putting this like Pa by RU2, I can write down minus dAb MWA by RUT, this is nothing but your dPa by dy, right. So, MW A by RUT, if you look at, so if I will take this inside, right, what it will be? It will be, we know that basically rho A will be Pa MWA by RUT, isn't it? So, therefore, I can write down here this, if I will take inside of this differential, because I will say it is not really changing with respect to that. Why? Because this is the isothermal, we are not considering there is a change in temperature, and then however, then I can write down m dot A is nothing but dAb into rho A by dy, right. Let us say this is 2, keep in mind that this rho A is nothing but your mass transfer per unit volume density, right, mass per unit volume, and dAb is the molecular diffusivity, and whose unit is meter square per second, right. And of course, we know that rho Ya, I can express this in the terms of Ya also. Ya, what is that? Rho A by rho, yes or no? So, I can express this expression mass flux A minus dAB rho YA by dy. Now, that again also we will have to find out, you know, how we can get the values for diffusivity, right. That is a very important point, we need to look at it. But let us now basically summarize what we have learnt, okay, and also look at in a very, you know, compact forms and find out whether it is similar, you know. If you look at Newton's law of viscosity, this what you call is a tau, that is your shear stress, and this is momentum diffusivity, and rho b is the momentum per volume, right. And this alpha for the you know, Fourier's law of conduction is a heat flux, right, and alpha is the thermal diffusivity, and of course, this I have given the CV at T, I will be using internal energy per unit volume. You can say enthalpy per unit volume also, right. For this case we are considering both are same. And so for this Fick's law of diffusion is concerned, and this is m dot triple dash I dij, and this is rho I, basically mass per unit volume of is species, right. Now, I can write down that as a, you know, single you know, equation, similar format. I can't say single equation, rather a compact format, that is theta is equal to minus d, you know, d psi by dy, and theta, if you look at what is the theta, theta is basically the flux, you know, flux, because the shear stress is nothing but your force per unit area, right, and heat flux, right, q dot double dash is heat flux. So, I can say the flux related to what, it can be mass, momentum, right, not together, or okay, mass or momentum or energy, any one of them, right. And psi, if you look at, is basically the properties, it can be mass, momentum or energy, right. So, you can write down in a very compact, you know, what you call format, right. You can just substitute these values, you can keep in mind that these you know, we will be finding out, we will be using this relationship, and it is very easy to remember this, you know, because of this very simplified form of that. However, these all these units are what? It is meter square per second, all this is diffusivity. One is momentum diffusivity, thermal diffusivity, and then molecular diffusivity. And we will see later on that we do use some non-dimensional numbers, parameters, right, and so that it will be easier to handle, right. One we will be using is Prandtl number, right. That is nothing but your momentum transfer, right, divided by the heat transfer. And nu by alpha, right. There is also another number which we will be using is Schmidt number, is nothing but your momentum diffusivity. I can put that way, actually it is not, instead of transfer I would like to put it as a diffusivity, that is better. thermal diffusivity, not heat diffusivity. This is again the momentum diffusivity by the mass diffusivity, right, d, and there is of course Lewis number is alpha by d, right. This is a thermal diffusivity, right. And mass diffusivity. Keep in mind that this is both d are same, like I am saying d is equal to d, I am using that. Okay. So you can get a relationship, right. Basically if you look at Lewis number, I can write down as Schmidt number, right. I can write down nu by d by nu by alpha. Okay, this will be, so this is nothing but your Schmidt number, like I can say this is as a Prandtl number, this is as a, and this I am calling as a Lewis number. So nu by d is nothing but your Schmidt number, and then nu by alpha is nothing but your Prandtl number. So I can write down as Lewis number, Prandtl number is equal to Schmidt number. Now question arises how we can really determine these properties from the molecular theory of point of view, right. That is the very important point what we need to look at it. So because these are the properties what we, the thermal diffusivity, mass diffusivity, and then what you call momentum diffusivity. But however, we will be more interested in what are those properties, like your viscosity, conductivity, and the what you call the mass diffusivity, right. So for that what we will have to do, we will have to basically invoke the molecular model of the transport process. That means the what we have looked at, kinetic theory of gases, we will have to look at that. Let us consider a cube and where these molecules will be moving, like this will be moving this direction, right, and kind of thing. It will be moving at a very different velocities, it will be in random order, right. All will be moving at different velocity in different direction, that it will be in chaotic in nature, right. And there will be basically complete disorder the way we operate, particularly our traffic in Kanpur will be in a chaotic sense. Similarly, molecules will be moving in a very chaotic way. But however, there will be some order, right, because it will be going and colliding with the surfaces. For example, there is a surface here, right, there is a surface, total 6 walls are there. If I consider a surface like that, let us say surface in between, right, this surface, what will be happening? The molecule will be going and acting, like bombarding, imaginary surface you can say, and then there will be change in the momentum, rate of change of momentum will be there will be some pressure which will be acting, there will be also some molecule as moving, so that there will be change in the energy level, right. Similarly, there will be transport of the what you call molecules, right, because and that depends on what? That depends upon the velocity. And when it is moving, we know that it will be moving with the various velocities, like RMS velocity we have considered. It will be also we can think of something average velocities, isn't it? And we can think of something what we call probability of velocities, right? Most probable velocities. So if you look at generally, because this molecular motion will be in chaotic in nature, right? Molecular motions will be in chaotic in nature, right? So therefore, what will be happening? We cannot really deal with the molecules. So for that, we will have to look at some properties, right? We will have to use the statistical tools, right? You can handle this statistically. And when we handle this statistically, so we have looked at Maxwell-Boltzmann distribution, right? Maxwell, right, distribution. That we have already seen. I am just again rewriting the distribution, right? mw by 2 pi RUT. Of course, V square, keep in mind that V is the molecular speed. And if you take these average values, you will get basically V average, what we will be dealing with average values, which will be nothing but what we call root over 8 RUT by pi mw. I can write down also 8 kb. Kb is your Boltzmann constant into pi by mass, right? Mass is the m is the mass of molecule, right? And keep in mind that in this, whenever it is moving, and there will be some kind of average properties which will be coming in any plane, regions, and this will be dependent on what? These properties, rate of change of momentum, or there will be molecular exchanges taking place between what we call layer to layer. Let us say this is one layer, there might be another layer, there will be some continuous properties which will be there. It will be continuous, but in the molecular sense it will be random. Are you getting? For example, each individual we are in a random fashion, but when you look at a nation or some state, it will be some pattern you will be getting. So these kind of things which will be in the macroscopic level, but in the microscopic level, but when you talk about in the macroscopic level, there will be some kind of properties, right? And then that will be dependent on what? Or transport of this momentum, mass and energy will be dependent on what? On the average molecular speed of the, right? Average molecular speed, and also it will be dependent on the collision distance, or what we call mean free path. If the what we call molecular speed is higher, that means there will be net flux will be higher. If molecular free path will be higher, average molecular free length or free path, if it is higher, what will happen? The flux also will be higher, right? Now we need to basically now consider this thing and find out a relationship between what we call these properties with this molecular speed and the mean free path. For that we will derive a relationship between for the mean free path, isn't it? Because we have not derived relationship. For that purposes, what we will do? We will consider that you know, like a simple case in which single molecule, all molecule will be identical with the same diameter, right, of d traveling with a molecular speed, average molecular speed V average, right, V average kind of things, and then we will consider that. So that then we will derive a relationship between the molecular diameter and then number density and then what you call and relate that thing to your mean free path. So that we will do in the next lecture, and later on after that we will be looking at basically how to relate these things to the your properties, right, that we will be doing.